Hello students, in this video we are going to discuss about the ionization constant of weak acids and bases. First, let us discuss for weak acids. Consider a weak acid HX that is partially ionized in an aqueous solution. Now what is this partially ionized? For example, if 100 moles of HX, that is, let us take any acid, HCl, HBr, HI, anything. If 100 moles of HX is taken and if it is in the aqueous solution, only the 10 H plus and X negative 10 X negatives are formed. That means from 100 mole of HX only the 10 mole of HX get ionized. So the remaining 90 HX are remaining, that is not ionized. So such type of ionization is called as partially ionization. That means the fully whatever the moles of acids are taken, that is not ionized. Only a part of that is ionized. That is called as partially ionized in the aqueous solution. As already we have discussed that weak acids does not undergoes the complete ionization. The weak acids does not undergo complete ionization. That's why they are weak acids, and the strong acids undergoes the complete ionization, that is 100% ionization is taking place in the strong acids. So in this we are going to express the ionization constant for such type of acids, that is weak acids. So let us, we are considering an acid that is HX, which is a weak acid, so in which is partially ionized in the aqueous solution, and this equilibrium can be expressed by this relation, that is HX plus water giving rise to H3O plus. Why it is giving H3O plus? Because here it is an acid HX, therefore it donate one proton to the water. So what is formed here? The HX become X negative after donating H plus, and the water that is accepting the proton H plus, that is giving rise to H3O plus, that is H2O plus H plus, that is giving rise to H3O plus. So once again I will tell here, H3O plus can be written as H plus also. We can write H plus also. So in this reaction, let at the initial concentration for HX, that is C, let C is the initial concentration, that means before the ionization, the concentration of the weak acid taken as C, because initially there was only reactant, no product. Therefore at the initial concentration we can say that the concentration of product is 0 and the concentration of reactant is HX, and here the concentration of water we are taking as a constant value. Next term, but alpha is the extent of ionization change, that let the extent of ionization, that means how much is ionization is taking place, that is represented by alpha. So what will be the decrease in the concentration of the reactant? Because when this reaction moves in the forward direction, there is decrease in the concentration of the reactant, and there is increase in the concentration of product. So let alpha is the extent of ionization. So how much is the decrease? That is C alpha is the decrease. Decrease, that's why it is representing by negative sign. And here there is increase in the concentration, because we have already learnt there is increase in the concentration of product side when the reaction moves in the one direction. So let C alpha is the increase, and here also C alpha is the increase in the concentration. So what will be the concentration at the equilibrium stage? That is equilibrium concentration is equal to the initial concentration, and how much is decreased? That is C alpha is decreased for the case of HX. So that is C minus C alpha. that is the initial concentration minus how much is the concentration is decreased. But in the case of product, how much is the initial concentration? That is 0 is the initial concentration. How much is increased? That is C alpha is increased. So the remaining part, that is how much initial plus increase is the C alpha. So that is 0 plus C alpha that we are getting here. Similarly for other also 0 plus C alpha giving rise to C alpha. So this is the initial concentration, that is for Hx, H3O plus and X minus. The initial concentration is C, 0 and 0. Then let decrease in the concentration. Here it is C alpha, here is the increase C alpha, here is the increase C alpha. So what is remaining at the equilibrium condition? That is initial minus how much is the decreased, and here there is increase, therefore the initial plus the increase, initial plus the increase, that's why we are getting in this way. Now if you wanted to write the equilibrium constant Kc for this equation, how you write it? That is Kc is equal to concentration of the product, that is H3O plus into concentration of X negative divided by Hx, that is concentration of Hx and concentration of water. Here the concentration of water is taken as constant value. So the concentration of water is taken on the side, and that is both together, that is Kc is a constant and concentration of water is a constant. Together we can take a new constant, and this new constant can be represented by Ka. Now what is Ka? Ka is equal to concentration of H plus, that is the product, as I told you. H3O plus can be written as H plus, and here the concentration of X negative divided by the concentration of Hx. So water we are taking as a constant, and that we have taken with Kc. So Kc and concentration of H2 together we are taking a new constant Ka. Now what is Ka here? Ka is called as the dissociation or ionization constant of acid Hx. Now we got the ionization constant for the weak acid, that is represented by Ka, and its formula is given here. What is that formula? That is the ionization constant of weak acid can be represented by formula, that is Ka is equal to concentration of Hx into concentration of X negative by concentration of Hx. This is called as a dissociation or ionization constant of the acid Hx. Now here we have already find out the value for the concentration of H plus, that is this value. This is the value. Concentration of X negative is this value. Concentration of Hx is this value. So we'll substitute these value in this. So what we'll be getting? We'll be getting in this way. That is concentration of Hx and X minus is C alpha. That is C alpha, that is the C square alpha square, C square alpha square divided by C minus C alpha. That we are writing in the, we are taking C as common. So C in bracket 1 minus alpha. Now from here, one of the C we can cancel it, because on the denominator side there is one C, and on the numerator side there are two C's. So one C we can cancel it. So what will be getting this? We'll be getting in this way, that is Ka is equal to C alpha square by 1 minus alpha. Now this is the formula which we need to remember here, that is ionization constant for the weak acid when its initial concentration is known to us, and if we know the extent of ionization alpha, we can find out Ka by this way. Or if we know the value of Ka, we can find out the value of extent of ionization if the initial concentration is known to us. So this formula is important to learn. So here at a given temperature T, the Ka is the measure of the strength of the acid HX. That means larger the value of Ka, stronger is the acid. So at a given temperature, this value, that is the value of Ka, is a measure of the strength of the acid. That means whether the acid have greater strength or not, how we can identify it with the value of Ka. That means if greater is the value of Ka, we can say that that acid is stronger. If the value of Ka is lesser, we can say that that acid is a weaker acid. So on the basis of the Ka value for a particular acid at a particular temperature, we can identify whether the acid is strong or weak. So that can be explained with the help of a chart which is given in the textbook. Some of the important acids are given here and its value of Ka is given here. So when you compare the values here, we can see that HF, the value of Ka is given to us, and HNO2 like this. So we can say that when the value of Ka is greater, we can say that acids will be the stronger acid. Let us take the phenol. The value of Ka is very less, so that means that is a weaker acid. And if the value of Ka is greater, we can say that will be the stronger one. So on the basis of the Ka, that is the ionization constant of weak acid, we can say that the acid is stronger or weaker. But if we take a log of that is a negative log of, when we take the negative log of Ka, then we can call that term as pKa. So if pKa value is greater, it means that that will be a weaker acid, because Ka, as we have already discussed, Ka is greater will be the acidic strength. But what is pKa? It is the negative log of Ka. That means it is the inverse value of, we can say that not just inverse, it have an inverse relations. That is, if Ka is greater for an acid, for that pKa value will be smaller, because pKa is the negative logarithm of Ka. So from this, what we can say that for an acid, if pK value is greater, that is a weaker acid, because they have smaller Ka value. Next, that is ionization constant for weak bases. For the weak bases, we need to find out the ionization constant. The ionization of the base MOH can be represented by this equation, that is MOH in the aqueous condition, that is it ionizes to M plus and OH negative. So what will be the value of equilibrium constant? That is Kb is equal to M plus OH negative by MOH, that is the concentration of product by concentration of reactant. So Kb is equal to M plus OH negative divided by MOH. So in this case, here Kb is called as the equilibrium constant for the base ionization is called as the base ionization constant, that is represented by Kb. In this case, the equation that is given equilibrium reaction which shows the ionization of the base. For this, the equilibrium constant can be represented by this formula, and here the equilibrium constant is nothing but the base ionization constant, which is represented by Kb. Just now we have derived a relation, that is Ka for the acids. Similarly, when we do for the bases, we'll be getting the formula in the same way how we got the formula for the case of acid. That is the same formula here, but here instead of Ka, we have to use Kb. So Kb is equal to C into alpha square divided by C into 1 minus alpha, where C is the initial concentration, alpha is the extent of ionization, and Kb is called as a ionization constant of weak acid. So when we take the negative log of Kb, that we can use the word here pKb. So if value of Kb is greater, we can say that that will be the more stronger base if the value of Kb is greater. But if the value of pKb is greater, that will be weaker, because the pKb is a negative log of Kb. So greater the Kb, greater will be the stronger will be the base. And if the value of Kb is greater, automatically the value of pKb will be lesser, because pKb is negative log of Kb. So the value of a Kb is for some of the bases, it is given in the textbook in a tabular form. So all of you look at these values, and these values will help to predict whether the base is stronger or weaker. That is depending upon the value of Kb. Greater the value of Kb, greater will be the basic character. Now let us derive a relationship between Ka and Kb. So what is the relation between these two? That is Ka into Kb is equal to Kw, where Ka is the ionization constant of the weak acid, Kb is the ionization constant of the weak base, and Kw is the ionic product of water. So the derivation of this relation I'll be sending in the form of images, and through explanation will be done in the audio form. So here, when we take a negative logarithm on the both the side of this equation, then we get the pK value of the conjugate acid and base are related to each other by this equation, that is equal to pKa plus pKb is equal to pKw, that is equal to 14 at 298 Kelvin. We have already derived a relation, that is pKw value at 298 Kelvin, its value is equal to 14. So when we take the negative log on both the side, so negative log of Ka, that is nothing but we can take as pKa, negative log of Kb can be taken as pKb, and negative log of Kw will be taken as pKw. And when we apply the log, so the product will be getting into the positive sign. So as a log of A into B, we apply the formula, that is equal to log A plus log B. That's why here there is a multiplication, because we are applying this formula log A into B is equal to log A plus log B. So that formula we are applying. So negative log of Ka into Kb, that is equal to negative log of Ka plus negative log of Kb, that is equal to negative log of Kw. So that is nothing but that is equal to pKa plus pKb is equal to pKw. So this formula is very important to learn. This is the relationship between the values of, that is the pK values of conjugate acid and the base, that is related by this equation. Now let us do the text solved problem. We'll be doing here, that is problem 7.20. Calculate the pH of 0.08 m solution of hypochlorous acid, that is HOCl. The ionization constant of the acid is given here, that is 2.5 into 10 raised to minus 5. Determine the percentage decomposition of HOCl. So here we are doing this problem. In this, the weak acid is given and its initial concentration is given and the ionization constant is given. So we'll be using this in this way. That is, the first we are writing the equation for this one, that is HOCl plus water give rise to H3O plus plus ClO negative, and the initial concentration of HOCl is given to us, that is 0.08. So what is the initial concentration of product? That is 0, because at initial stages the concentration of product is 0, that is it is written as 0 here. Now let X is the decrease of the concentration of the reactant. So what will be the increase? X will be the increase. So at the equilibrium condition, the concentration, that is equilibrium concentration, now it become, that is the initial minus the, how much is decreased? That is X is decreased. Let X is the decrease in the concentration. So how much is remaining? That is 0.08 minus X. And here how much is remaining at the equilibrium stage? That is 0 plus X. Here also 0 plus X, that is represented as X. Now in the formula of Ka, we have substitute the value of concentration of H3O plus and ClO negative, that is X here and X here. So we are getting X square divided by concentration of HOCl, that is 0.08 minus X. So we are substituting here. So when we solve here, but here the X value is very less in compared to 0.08. Therefore, we'll be taking 0.08 minus X can be taken as 0.08. So when we solve this one, we'll be getting the value of X, that is nothing but the concentration of H plus, that is 1.41 into 10 raised to the minus 3 m. The m is the unit mole per liter. So now we need to find out the percentage dissociation. So percentage dissociation, how we can find out how much is the HOCl get ionized. That is the HOCl that is ionized, we can write it as dissociated HOCl divided by initial HOCl into 100. As because we are finding out the percentage, therefore it is need to multiply with 100. So here the HOCl that is dissociate is nothing but the concentration of H plus that is formed here. We have find it out. So that value divided by the concentration, initial concentration, that is known to us, that is 0.08. So into 100, when we solve this one, we will be getting the value 1.76 percentage. That means this acid get ionized by 1.76 percentage. We need to find out the pH also. So what is the formula for pH? pH is equal to negative log of H plus, that we have already learned the formula. pH is equal to minus log of concentration of H plus. So what is the concentration of H plus? We have just now find it out the value, this value, that is 1.41 into 10 raised to minus 3. So when you solve this one, we'll be getting the value 2.85. So in order to solve this one, the logarithm table is needed to solve this value. So here in this video, we have discussed the ionization constant of weak acid and the weak bases, and the relation between the weak acid and weak bases, its ionization constant, that is Ka into Kb is equal to Kw. And we also solved one problem related to this. So this is all about this video. Have a nice day.